to Engineering Tomorrow, and we have a really good session in store for you. It's our robotics session. And what I really love about this session is we're learning how to make systems and processes we deal with every day a little easier by using a robot, by using something that's intelligent. Isn't that really cool? I want to give a shout out to the group that helped develop this lab, a good friend, Christine Boudel, but also students, because we do want this to be relatable to you. And we spent some time just updating this lab just a little bit to really infuse the essence of robotics, sense planning, and acting. And I want to thank this team as well for their contribution. Hey, before we jump in, you're probably wondering, who is this guy? Let me tell you a little bit about not just my space journey, which I have on this page, but also my robotics journey. So I started working on spacecraft like SDO, which is all about the sun, and LRO, which is all about the moon, and Da Vinci, which is really all about the stars, and even the magnetosphere multiscale mission. I love those missions. But these missions, some of them are really hard for a human to operate and to run, because there's very difficult processes we have to complete in space. Think about the James Webb Space Telescope and it just opening those huge thermal shields. So humans in space, they're very important. There's things that astronauts, it's just difficult for them to do. I mean, I was in love with wanting to become an astronaut. My favorite astronaut, his name is Melvin. And I just thought, man, this guy, he's the best. I wanted to be him. And then I realized something. For us to go to the next level in space, for us to accomplish what's impossible, we're gonna need some robots. We're gonna need some systems that can perform things that humans, it's just a little too hard. And maybe those planets are just a little too far for us to journey at this point, right? So that's why I got my master's in robotics at Johns Hopkins and in project management. I know some of y'all are thinking, man, this guy went back to school. I know. Yeah, but I needed to learn something about these robotic systems so you can achieve things like you see on this page. Think about the Mars rover. Think about the quadcopter that's on Mars. It's crazy, right? Also, these robotic arms that have allowed us to, you know, improve the International Space Station. That's all through robotics. So if you're wondering that what is a robot, well, let's talk about that a little bit on this next page. We're going to show you a video about robots and what robotic engineers do. And then on the backside, we'll talk about some things that you learned. All right.
My name is Tessa Lau. I am Chief Robot Whisperer at Savioke. Savioke is a robotics company, and we're building autonomous robot helpers for the services industry. I went to Cornell for my undergrad. I got a bachelor's in applied physics and computer science. I really liked physics because it was about hands-on doing experiments and building things and making stuff real. Computer science was also really interesting because you could create stuff a lot faster on a computer. And so I went into computer science for my graduate studies. I went to University of Washington, where I studied artificial intelligence and human-computer interaction. I don't think of myself as a roboticist, even though that's what I do. The robot whispering for me is about making it so that the robots behave well in human environments. And it's not just about programming or engineering, it's about looking at those robots in context. The way he's being used is that the front desk receives a call from a guest room saying, I'd like to order a sandwich, or I forgot my toothbrush. And so they grab the item that they want to deliver, load it into the robot, type in the room number, and the robot will go off to the room automatically. Robotics has the potential to actually change people's lives in a much deeper, fundamental way than software could, because robots are physical. They can actually move around in your world and do things for you. The robots that we were building, they can't replace a human because there's so much that a human can do that a robot can't. What they can do is the mundane stuff that no one wants to do anyway, like, run stuff up to a hotel room and then come back down. No one person can build a robot on their own. And we all know that, and we all help each other out. I think one of the biggest skills that I bring to Savioke is soft leadership skills. I'm invested in making sure everyone's working together. I think it's really valuable to know a lot about a variety of things and then have a specialty within there where you focus and do a deep dive. I know computers, I know networking, I know physics, and that actually gives me knowledge about mechanical performance and just the basics of electrical engineering. I do a lot of integration testing, just making sure all of our software works properly on the physical hardware. We use GitHub a lot, which is an online collaboration tool for sharing source code and commenting on it. We're leveraging a lot of the contributions from the open source community. Those tools are freely available. Anyone can pick them up and learn how to use them. My advice to women going into STEM field is don't listen to anyone who says you can't do something. Definitely cultivate hobbies related to the field that you want to be in. I was lucky that my dad was into hobby computers, and so he brought one home, and so I would spend a lot of time just playing around with the computer and seeing what it could do. We have those robots out in hotels right now. We can log into them over the internet and watch them as they're doing deliveries to hotel guests. Seeing the people interact with them and be delighted, all of those interactions are happening because of things that I built, and that's really incredible.
What were some key components of a robot? What do robots perform? What do some engineers do that are involved with robots? Something I hope that you caught from that video is robots can perform many of the daily tasks that we need to perform as they learn and become efficient. They can cook. They can perform surgery. I mean, just imagine how critical how our bodies are so intricate, how critical it is to perform those steps along with doctors very efficiently and accurately. And then simple tasks like folding clothes. Those are all different things that robots can do that they can be trained to do and then perform on their own to make our lives just a little bit easier. And that video talked about what engineers do and maybe some components of robots. But we also want one more video before we jump into this lab that talks more about how robots work and what are their components. So after this video, we're going to talk a little bit about the three components of the robot. So try to think about that. What are the main three components that define the essence of a robot?
Someday in the near future, you might be wandering around town at night when out of the blue, you'll stumble across a robot. If that happens, maybe you shouldn't be too surprised. Not so long ago, robots were mostly found in the realms of science fiction. Today, they're vacuuming floors, building cars, and even roaming around the surface of Mars. Robots are still pretty far from having a human-level capacity of intelligence, or even dexterity for that matter, but they're already a big part of many branches of engineering. In the US, over 100,000 robots have been added to factory floors since 2010. Knowing exactly what robots are, what they can do, and how they work is more important than you might think, because soon they might be living among us. The classic picture of a robot is something with human-like intelligence and maybe even a humanoid appearance. But like so much else, real-life robots aren't much like what you usually see on TV. Robots come in all shapes and sizes, and they can be built very differently depending on what they're used for. For example, some of the robots used in mining are made from a camera mounted on a small chassis with wheels. That allows them to enter and inspect mine shafts and even retrieve leftover material from places it's hard to get people in and out of. Meanwhile, in medicine, specialised robotic arms, with a bit of human assistance, can perform precise surgeries through the tiniest incisions. There's also a difference between robotics and artificial intelligence, or AI, which people sometimes confuse. While some of the concepts are similar, robotics deals with a specific set of ideas, although it does borrow a few from AI. AI deals broadly with the goal of automating decision-making for complex tasks, the kind you can't write a simple set of rules for. That could be everything from playing chess to driving cars. Right now, AI systems tend to have very narrow goals, but the holy grail of AI is to develop a system that can make intelligent decisions about any sort of task using different sources of information. Our focus will be on robots which are designed for more specific purposes in the physical world. In engineering terms, a robot is a machine designed to interact with its environment, make an appropriate decision based on those surroundings, and then carry out the jobs related to its goal, all automatically, which means a true robot doesn't require a human controlling exactly what it does. In general, the field of robotics also deals with machines that do all of the same things, but might require a human operator to carry out some tasks. Whether fully automatic or not, virtually all robots have a few features in common. First, robots are machines made from materials that occupy physical space, so they're more than just lines of computer code. That's one of the key features that distinguishes them from AI, although computer engineering is important for robots as well. Second, most robots have some way of sensing features of their environment, usually by measuring light, sound, or force feedback. They can then use that information to make a decision about what to do next, depending on what they're designed for. The tasks robots are built for tend to be complex, requiring a sequence of different motions. So an automatic door that opens or shuts in response to whether you stand in front of a sensor wouldn't be considered a robot. The tasks that robots handle are more sophisticated, like welding two intricately shaped pieces of metal together. Third, to interpret the signals they receive from their environment and coordinate some sort of response, robots have computers built somewhere into their design. These work just like any computer, taking inputs and delivering outputs. But unlike most ordinary software, the software on a robot's computer generates electrical signals that are directly passed onto the robot's hardware, instead of just changing information in a file or on a screen.
That was a great video. I told you. Wasn't it a great video? So if you had to nail the 3 components that define a robot, what would it be? If you said sense, plan, and act, you are spot on. You've got it. In that video, it talked about sensors, maybe optics, or sound, or sonar, or LiDAR, what you've seen in the Tesla, right? Planning, that's the processing, that's the computer, the thinking, just like we all have a brain. It's a plan. And then all that has to come together in how the robot acts or how it responds to the stimuli in its environment, sensing, planning, and acting. Now, that plan is really the core of everything that's important about a robot functioning similar or in a similar manner to which a human functions, right? And it does that through something we call an algorithm. It's some processes and steps, ordered steps that ensure that it does sense and that information gets to the computer effectively. And it does act in a manner that it all comes together inside of that computer, inside the plan of the process. So we're going to talk a little bit about algorithms, and this lab will introduce us to computer science, which utilizes algorithms to perform various operations and steps. But before, I want to talk to you a little bit how we got here. Like, what's the history of programming and algorithms? Well, first, there's this program called Ada, developed by someone named Ada, and it was the first programming language used to solve some complex problems. Even people working together just couldn't work these complex issues, and it solved that problem. And then, programs really started to progress because once they learned you could solve a complex problem with programming or algorithms, they started to think, where else can we apply this? You may know this as well. All of your fun computer systems, the PS5, your Xbox, anything like that, it's all enabled through an algorithm, through programming. That's the essence of what gives us the games that you and we ultimately love, right? So there was the first 1 million computer programming related jobs now. There's a lack of programmers in our country, and there's 1 million computer programming related jobs. We need you to be learning this type of material for sure, right? So this is why for our day, what we're going to do in this lab is introduce you to this topic. We love to introduce you to topics through activities. So let's have a programming activity. And the purpose of this activity is to get our minds a little more in tune with what they call pseudocode. So I'm going to give you your first sample of coding in programming. You ready? Take out a sheet of paper and a pencil or a pen, and I'm going to give you some instructions. The key to any program, any robot, is good instructions. So here's your first instruction. Are you ready? Draw a large circle in the middle of your sheet of paper. You got it? Good. All right, now draw a triangle on top of the circle. Maybe it kind of looks like a birthday hat. I don't know. Okay. All right. Now, to the left of the circle, draw a rectangle. It's a thin rectangle. Beneath the circle, draw another rectangle, but it's a thicker rectangle. What else we have? Oh, in the middle of the circle, like a smiley face. On the left side of the circle, draw what looks like someone winking. Another squiggly line, a curve. And then to the right of the circle, we need one more squiggly line. You all done? Okay. Does your rendering look like this? It doesn't. No, I'm just joking. That's the point. Programs are only as good as the instructions you give them. Sometimes they call robots dumb because robots are only as good as we program them, only as good as the algorithms, only as good as the pseudocode. You got to develop good code if you want them to function properly. I gave you terrible instructions. Squiggly line, smiley face, nothing definitive, nothing quantitative, right? See, if this were a robot, you wouldn't say, hey, go over there, grab my cup. It needs to know this. Move forward 12 steps. Turn right 90 degrees until you reach some other objective that it can sense. So the lesson here is you gotta communicate what the robot needs to do effectively through your program. All right. And we're not gonna leave you alone. We have a whole process that you can use to kind of help you develop a good algorithm. Here's some good things. Shorter is better. Focus your code, one function, one activity, move forward X amount of steps, focused, succinct, right? That's important. Then, other thing is start with what problem you're trying to execute. Like, is this the robot that is going to make me some food? Is this the robot that's going to do my homework? Everybody wants a robot, right? And then you work on your design, and then after you work on your design, which is your pseudocode, then you start your program. Then you actually start putting your blocks in or writing your text-based code. Okay, and here's another nice tool: debugging. You want to really write your code, just a little bit of your code, and then kind of debug and troubleshoot, see what the program tells you about what's wrong with it before you make 1,000 lines of code and it's hard to figure out where you messed up. You want to iterate, step by step. I'm going to write a little code, test it. Oh, that worked. Then I'll move to the next step. That's what we want you to do. So we just gave you a few tools before we jumped into the lab. Now you probably wonder, well, what am I going to do in this lab? Well, of course it has something to do with a robot, and you're going to use loops. You're going to use conditionals and maybe even variables. And then after this is over, we'll talk about an extension activity that'll challenge you a little bit more. And the program that we're going to use for this is called Mblock. We're using Mblock because you could either download it or you can use it just on the cloud. So, hey, why don't we just step into Mblock real quick and play with our first program? We'll use blocks, but what we'll do is we'll just make a basic program and attempt to draw some shapes using that program. All right, let's jump into Mblock. All right, we're in Mblock. Isn't it nice? So check this out. We're doing some block style coding. Our first challenge, let's just draw, if we could just draw a line. And we're going to do that with our sprite. Our sprite is helping us just kind of navigate here through this page. This is where you can see your code in action. Later on, you'll see your robot in action. So we have our sprite. If you want to change that sprite, you go down to the add button. You also could change your background if you want as well. But let's get to it. How would we draw a shape? All right. First, we always start a program with an event. So our program knows exactly when to start. So when clicked, we're going to place that into our coding page when clicked. And anytime you're going to make your first artistic creation, it's nice to start on a clean sheet of paper. So let's go to our pen and we're going to start with an erase all. Okay. And to start drawing, we're going to place our pen down. So let's add pen down. You good? Oh man, we're cooking now. So how are we going to draw? Where our pen, oh, let me get rid of pen down. You should have told me that. Pen up. It's pen down. We don't want to lift our pen up. Pen down. That's good. And now we're going to go to motion. Let's go to motion. And if our pen is down, if we just move a certain amount of steps, we should see the sprite creating something. Let's choose move and let's move 100 steps. Let's actually see this. So I'm gonna press play now. Bam. Oh, look at that. It wrote something. All right, good. Now let's add a turn. Okay, I'm gonna add a few more steps, and I want you to predict for me what it does, what the code is gonna do when you add some steps. Turn 90 degrees. All right. And then I'm gonna move another 100 steps. I'm gonna turn another 90 degrees. Ooh, are you thinking? What's happening here? Let's move 100 steps. Oh, I bet you're thinking of it now. I'm gonna turn 90 degrees. One more time. Move 100 steps and turn 90 degrees. If you had to predict what this sprite, what this program is going to create, what would you say? Think about it. What is it doing? Okay, let's see. Ah, it created a square. Why? Because the code says move 100 steps, turn 90 degrees. Are you thinking geometry? Move another 100 steps, turn 90 degrees. Move another 100 steps, turn 90 degrees. Each one of those blocks is a function, some simple activities, some simple steps to perform a specific objective, to turn or to move forward. That's pseudocode, right? And then you also may use in this some conditionals. Let's say you wanted your robot to move to a certain point, but only if it saw something. You need a conditional in that case. And then maybe there is some variables you want your robot to utilize. A variable is something that you would change. So you can actually have variables in your code that may say, I don't want you to move the same amount of steps every time, right? I want you to move maybe less steps under these conditions. Those are all the things that you're going to play with in your program. Finally, you're probably thinking, hey, Milton, you did a move, a turn, a move, a turn, a move, a turn. Isn't there a way to simplify that? Yeah, you're right. Let's see if we can go through these different programming options and find like a loop, okay? Let's see if we can find a loop. There it is. This is a loop. Instead of using all these different programs, all these different steps, all right, we could take out our move. We could take this repeat and then maybe just repeat it 4 times and perform the action all over again and get the same program, get the same outcome. That's important. Loops. There's different kind of loops. There's these repeats. There's these loops that are forever. And then there's some kind of waits and whiles. And we'll talk all about that when we jump right back into our presentation. Mblock, isn't it fun? That was great. You drew a shape. That's essentially what you did. And what you did, just a little recap of it, is you used a function. That function is that the block that allows you to perform a specific activity. So we used a function to draw a shape. And one thing you learned in drawing this shape is that you have all these different steps that we performed. Move, turn, move, turn, move, turn. But we could optimize that process by using loops. A loop is something that you can use to repeat that action over and over again. And all of that was kind of static, move forward 100 steps, turn 90 degrees. But what if you need your robot to vary that some, right? What if you don't want it to perform the same static, the same quantity of moves over and over again? Well, that's where you can use something like a variable. It stores that information and it references it so we can manipulate it or change it later on. For example, time. Time, right? And there's a step to making these variables. In Mblock, we give you just a few examples on how you can use a variable. And one thing you could do, here's an idea. See how quickly your robot can navigate through the maze by counting the time. That's one thing you can do to use a variable, and we show you here. All right. And then finally, we talked a little bit about decision making. What if? And an example I gave you for that was if the robot is moving forward and it doesn't want to keep moving forward, it wants to turn left, turn right, maybe even stop when it sees something. That's what robots do. That's why they use sensing of stimuli in their environment. We call those conditionals. If I do this, something else happens. If I do this, something else happens. And if I do something else happens. That's like a else if then. Okay. Here's a fun game we have for you as well to try as well. Try having this person that's swimming, or this animal stay within the pool. What kind of if then? What kind of conditionals would you use? Well, I want to keep swimming forward, and then if I stop seeing blue, but now I view or see or touch beige, then I want to turn around. And isn't that very similar to what you want to do if your robot is going to navigate through the maze, right? So our challenge, the main challenge, is programming your sprite or your robot to navigate through this maze. A little tough, right, man? How do I start? Well, don't forget about conditionals. Don't forget about your functions. Don't forget about variables. And don't forget about sensing. All those different things you can use. And here's an idea. If you bump into the wall, right? Turn left. So we have a loop. And if you bump into the wall, turn left. That's an example. Is it going to work? I don't know. Try it out. Engineer it. Okay. One more example. All right. So let's say instead you're like, I don't know if it's turning and moving correctly. Instead, you can add something called a random. It's going to kind of randomly choose how much it rotates or moves based on the conditional or the response. Try that out as it intersects with the wall or its environment or the map. It'll perform a random step. And I've given you a piece of this code, right? You got to build the rest. Okay. Well, this was really good. I enjoyed this session with you, all about robotics and algorithms and processes and systems. Remember, robots sense, plan, and what? Act. They use electronics and a computer and different sensors all coupled together to make processes, to make different things that we even do as humans easier, right? And even like you see in this image here, man, if someone had to investigate if there was some sort of bomb or danger, I'd rather have a robot doing that than a person. Okay. If you enjoyed this, oh man, continue to explore some things that are related. Artificial intelligence, man, that's another. Without the programming, well, I'll say without the electronics and without the sensors, artificial intelligence and machine learning are trying to make what we do a lot easier. You're like, well, artificial intelligence, machine learning. Have you heard of Chat GPT? Yeah, that it uses that space. Image recognition, facial recognition, it uses that, right? And then maybe you're into ultrasonic sensing, maybe you're into LiDAR, right? All these different things that allow the Tesla and other electric vehicles and even, internal combustion engine vehicles move and operate and drive by themselves. Well, what tools do you need in order to win in this space? Well, to win in this space, learning about robotics. I did some mastery work on robotics. That's great. Electrical engineering is always great. All the electricity and the current and the voltage you need to make the system work. We need power. Mechatronics kind of pulls all of it together, the mechanisms. Computer science, that is your pseudocode, your algorithms. And then finally, computer engineering is what I would recommend anyone major in if you're interested in this, because it brings computer science, it brings electrical engineering and all things engineering together to make you a really, really strong robotics enthusiast. Okay. Finally, we want you to kind of dive into your student interactive notebook, because we have a few different challenges based on your maturity or your experience with coding. So if you have some basic experience, we'll start you off with blocks in a simpler challenge. But if you have, a little experience already, don't worry. We have some good challenges for you, and we hope you're going to enjoy it. Well, thank you all so much for spending time with me in this introduction to robotics. I absolutely cannot wait to see what you create. On behalf of Engineering Tomorrow, thanks again. I can't wait to see you again. Bye.